Section 1.3, graphs of functions. So we're basically going to do what you've done in the past. We're just adding some new terminology in as well. So based off of the notes, you saw the increasing, decreasing constant, which we're going to practice that now. The even, odd, neither, and extrema. Extrema you've done in the past. So using your graphing calculator last year from Algebra 2. So we have 3 examples to do on the video themselves, and then we do have one that's going to be done in class that is extremely calculator driven, and so just want to make sure that we're all there together working on it. So we'll do these 3 and then we'll do that in class. So here we've got f of x is equal to negative quantity x plus 1 squared minus 2. Hopefully looks familiar to people. This is just a parabola. So I am going to go ahead and identify the important information. So I know that my vertex is going to be located at opposite the inside, exact the outside. I know that this is going to be opening down because of the negative in front, and I know that it's neither going to be compressed nor stretched because the coefficient in the front is just a negative and it's 1. So I'm going to take a second and graph this. Okay, now that I have my sketch of this graph, I should be able to identify everything else. Now, previously we talked about domain and range, so knowing that this is a parabola that opens vertically, I know the domain is all real numbers. You can plug in whatever you want. The range, well, taking a look at the graph or even looking at the equation itself, to be able to determine the range, I am going to look for where the vertex is. It looks like it's right there. And that's going to be the highest point where everything below it is going to be the rest of the graph. So my range, it's always going to be low to high. So the lowest this thing is going to go is negative infinity, and the highest it's going to go is the y value of the vertex, which is negative 2. But it does exist there, so make sure you put a bracket on it. Now, taking a look at this graph, the next thing that I want to talk about are my increasing, decreasing, and constant. So remember that these are intervals. These are intervals during which the during which the y value is either getting bigger, getting smaller, or staying the same. So if I take a look at my graph, if I come in from the left-hand side of this thing, so let's grab a color here. If I come in from the left-hand side, it looks like my y values are going to be increasing as I get closer and closer and closer to the vertex. Remember that this is the interval of the x's. So this is increasing as I come in from the left x's as I get closer and closer and closer to the x value of the vertex. But it's as it gets close to the x value of the vertex. It doesn't actually increase through the vertex. Then, immediately after the vertex, it looks like my graph is now going to be decreasing. So immediately after the vertex, as I approach the right side, my y value is getting smaller. So I'm decreasing immediately after the vertex as I go to the right. Now, taking a look at this graph, to be constant, and there's arguments about this in the different calculus and math worlds. I'm not going to get into that. We're just going to go ahead and think about the constant being a flat part. So it's a point at which the y value points, so a beginning and an end, where the y stays the same. Well, a parabola does not have that, so it's not constant anywhere. Then, the last thing that we need to take a look at is even, odd, neither. Well, even, odd, neither can be done a couple of different ways. One, you can just take a look at the graph. So, if it's going to be even, then that means that the line of symmetry for the parabola is on the y-axis. So I'm going to go ahead and put the line of symmetry in here. My line of symmetry for my parabola goes through the vertex here. If this parabola is going to be even, then that line of symmetry sits on top of the y-axis, which it does not. So this is not even. If this was an odd function, then that means that any point that exists over here, for example, so up in that top right-hand quadrant, would have a partner equidistant through the origin on the other side. So that means that I would go down 3 and left 2. So let's do it again. Down 3, left 2. These 2 points, so where my first x is and where my second x is, you would have to have points that line up exactly like that for the entire black curve of the graph. That's not the case either. So, based off of this, it's not even because the symmetry is not on the y-axis, and it's not odd because you don't have symmetry through the origin. It's actually very common that this is going to be neither. And the last thing that we need are extrema. So for our extrema, well, the extrema on a parabola, in this case, is the vertex. So the vertex was -1, -2. Okay, so here we have another function. Notice that this one is piecewise. So again, be careful how you graph this. Make sure that you obey the restriction. I'm going to go ahead and basically do the exact same thing that I did before when we did piecewise. So I'm going to grab a color and I'm going to let that represent the first piece here. So I want to make sure that I am less than -3. So I'm going to make a little table. With my function. My boundary is -3, and it's going to be an open dot because it doesn't have an equal to. Then I want to be less than, so that's going to be to the left. So let's plug in a -4 and a -5. Plug those in, create my table, and go ahead and get my graph going for this. So I'm going to pause for just a second, set up my graph. You might want to do the same and then check and see if we're the same for this first part. Okay, so my orange graph is now up. I started at the boundary with the -3. Notice that it's a hole because there's no equal to part. And then I went to the left, which was less. Now I'm going to do the exact same thing for the one in the middle. So let's go with, I don't think I've used purple yet. Just use purple. So I want to go from -3 to +1. Now this is pretty clear what my table is going to be. So, and then my y is just 3. So I've got -3, -2, -1, 0, 1. At the -3, it's going to be filled in because it's got an equal to part, but at the 1, it's going to be a hole. And then all of my y's are going to be 3. Since there was nothing for me to plug the x's into. So I'm going to pause, I'm going to graph, I want you to do the same, and then see how we match. Okay, so my purple graph is up there now. Notice that the hole for the orange has now been filled in for the purple. That's fine. So you can have a filled in circle filling in a hole that was already there. It's still going to be a function. That's not a problem. It really becomes an issue, though, when you have 2 solids lining up, which is not good because that's not a function. So now I'm going to move on to this next last part, and I'm going to pause it from here. So I would pause if I were you, set up your table, and then check and see if you and I match table and graph. Okay, so now I have, and I chose blue, so make sure that we have all, I have 3 different colors on here to make sure that you can follow with what I'm doing here. So now that we have the graph, I think we need to go through and identify everything else. So let's get rid of some of this graph since I don't think we need that much space. Give us a little bit more room to write. So let's see, what are the things that we needed to identify? We need to identify the domain and the range for the whole thing. So the domain for this whole thing, not just the pieces, I'm going to look at the graph. I don't see any x value that isn't going to be dealt with. So I think my domain is going to be all real numbers. My range. So I want to see how low this things go. Well, at first it looks like the vertex here might be the lowest point. But then I see the arrow over here. And this arrow tells me that this thing's going to keep going down forever. So I think the range is going to go as low as negative infinity. Then I take a look at the graph. At the top, and I see that straight line segment where the 3's are, but then I see the arrow over here on the parabola. That tells me it's going to go up forever. So negative infinity to infinity, or you can say all real numbers as well for the range. Then the next thing that we have is increasing, decreasing, and constant. Now, when there are multiple things that could be happening in a graph, I like to start from left to right and just see what's happening. So as I come in from the left, I'm going to be at the orange. It looks like this is increasing as I get closer and closer and closer to that orange-purple business that's happening. So I'm going to be increasing from negative infinity, far to the left, as I get super close to that x value where the orange and the purple come together. Remember, it's about the x value. The x value where the orange and the purple come together is negative 3. As soon as it hits negative 3, it's going to stay constant. Now, with constant, it's as soon as it hits the negative 3. So as soon as it hits it, as it approaches the x value where the purple and the blue came together. The purple and the blue came together where the x was 1, and it remained constant starting at and ending at and going through between negative 3 and 1. Then, as soon as I get to negative 1, it looks like I'm now going to be decreasing. So I see decreasing here. But only as I get really close to the vertex of the parabola. So I'm decreasing immediately after the constant, so 1, as I get closer and closer and closer to the vertex of the parabola. Well, the vertex of the parabola looks like it's at x equals 3. So I'm decreasing as I get closer and closer and closer to that x value of 3. Immediately after the 3, it looks like I'm increasing again. So immediately after the 3, so I go back to my increasing, put a comma. Immediately after the 3, it looks like it's going to increase forever. Then, for even, odd, neither, taking a look at this, I check to see if it looks like it's symmetric to the y-axis. I don't think so. For it to be symmetric to the y-axis, that means that if I put an invisible line down the y-axis, then the right and the left-hand side of the y-axis would match perfectly, which it doesn't. There's a straight line segment on the left, and there's a parabola on the right. Clearly not the same. In order for this to be odd, that means that every point in the upper right-hand quadrant would have to have a partner in the bottom left-hand quadrant. Where the purple and the blue come together in the first quadrant does not have a partner down in the third quadrant. This is not odd. So this falls into that category of neither, which a lot of things do. So this is neither. For these type of piecewise defined functions, we are not going to be discussing extrema. we will keep those to mostly polynomial functions, which this is not. So we're done with this one. Okay, last question for the video. We want to prove that a function of the following form is odd. So I would define the function as f of x equals, and that big huge mess. I think one of the things that we need to talk about first is what does it mean for a function to be odd? So, to be an odd function, I know that f of negative x is going to be equal to negative f of x. This is going to be the driving force behind this. So what I'm going to do is I am going to plug in this. So I'm going to plug in negative x for all x's and see what happens. I'm really hoping that it takes the original function and just flips all the signs on it, which means that it's going to be odd. Another thing that we need to know is what these 2n plus 1s represent. Well, n is going to be defined as an integer, which means that it is going to be from the set of numbers so on and so forth. Well, we need to be able to figure out what this means, because those are exponents for us. So if we wanted to take 2n plus 1, or 2n minus 1, or this whole cubed business, we need to know what type of an exponent this is going to be. Well, if you take any number at all, let's say that n is equal to 4. Then I know that 2 times 4 plus 1 is going to be 9, an odd number. If I take 2 times any even number, I'm going to get an even number. Then I add 1 to it, it becomes odd again. What if I start out with an odd number? Well, the same thing happens. Because this first part gives you a factor of 2, it's always going to be an even number. Take anything times 2, it's going to be even, except for 0, of course. Then you add 1, you get an odd number. So, with the idea of adding 1 or subtracting 1, same idea, you're always going to get an odd number. So what this means is that I have odd exponents. Now I think we can proceed with the proof. So what I'm going to do is I'm going to plug in negative x, and I want to see what happens here. So I'll take my original function. I'm just going to plug some negative x's in and see what happens. So I get a, nothing is happening here because those aren't x's. There's an x. Plus, just continue on. Everywhere that you see an x, plug in a negative x. Once I have those all plugged in, now I need to come and also come to the conclusion about what happens with a negative number when you send it to an odd power. Well, a negative number to an odd power is always going to be a negative number. So our term inside here, this whole negative x to the 2x plus 1, this is going to be a negative number. So I'm just going to take the negative sign all the way out in front, since it's just a negative number to an odd power. Same thing on the next one. It's going to be a negative number to an odd power. negative number to an odd power. Now, taking a look at this function, this is f of negative x. How does this compare to the original f of x function? Well, they look almost identical. The only thing that's different are all of the signs are negative. So I'm going to factor out a -1 from all of these. So I'll take out my negative sign from all of the terms and write down what I have. Just factoring out that -1. After I've done that, now I see how this compares to the original f of x function. Well, all of this in here was the original f of x function. So that's f of x. Now, drop down the negative sign and bring down the other side. Going back up, to determine it to be an odd function, this must be the case. Therefore, f of x is an odd function.